So having looked at the inductor circuit, we're now going to have a look at what the capacitor is doing in the circuit. Okay. Those of you that have done science for me in year 1 will remember some of this anyway. Hopefully you're remembering some of it. If we put a per capacitor in the circuit, and again that's not achievable because even the wires have got some resistance and bits and pieces. If we could, we'd end up with a current that leads the voltage by 90 degrees, or voltage lags the current by 90 degrees. Does that fit in with civil? Yes, it does. Yeah? Okay. The instantaneous current flow in I is given by the capacitance C multiplied by the rate of change of voltage. Okay. So what happens here is we get a voltage and a current in this circuit at 90 degrees out of phase with each other, but the opposite direction to that with the inductor. So they actually work in opposite to each other, these two components. Okay. So for an ideal inductor, the red one there is the current, the blue one is the voltage, and there's a 90-degree angle between the crossing points with the voltage ahead of in time, so the current leading the voltage, or the voltage lags behind the current. Yep. Again, we get this double pulse on power with the top half and the bottom half cancelling each other out. No overall power dissipated. And that's a little bit easier to understand with the capacitor, because if we look at the voltage going up here, we're charging the capacitor up, and then we're discharging it. Then we're charging it up and discharging it. That charge is this going backwards and forwards between the two plates and actually not doing any useful work. The only way it can do useful work is if the current that's charging it passes through a resistor, and we get some watts out of it. So a per capacitor uses no power. Takes it, gives it back. Takes it, gives it back. Charges up, passes it back again. Alright? So the power overall for a per capacitive circuit is 0 over time. It averages nothing over time. So we've got this quantity capacitive reactance. XC, it's measured in ohms, and you calculate it either by 1 over 2 pi FC, so again it's frequency dependent, or 1 over omega C, again where omega is always equal to the 2 pi f bit from the first half of the first version of the formula. So, with this 1 over relationship, the reactance of a capacitor is going to fall as frequency rises. Its impedance reduces as we increase the frequency. So what's going to happen with the current in this circuit if we change the frequency? If we put the frequency up, the current will go up. Yeah? Because the reactance or the impedance is going down. So the inductor and the capacitor work in opposite to each other in the circuit. As one's rising, the other one's falling, and so on. We'll use that fact to good effect in the next learning outcome when we talk about filters, which are a device for filtering out certain frequencies in a circuit. So we can use combinations of resistors and capacitors to create a filter that will allow certain frequency AC to go through and will block other frequencies. That's what we're going to be doing in a couple of weeks' time. Okay. So for a 100 microfarad capacitor, That's how the reactance changes with frequency. At 60 hertz, 26.5 ohms, 120 hertz, 13.3 ohms, 2500 hertz, we're down to less than an ohm. So if we look at an actual circuit, we've got a 10 volt applied voltage at 60 hertz, 100 microfarad capacitor. That has a capacitive reactance of 26.5 ohms. And we can work out the current in the circuit. I is E over XC, 10 over 26.5. 0.377 amps. That's the magnitude of the current. But what we should really be doing here is taking into account that I and E should be 90 degrees out of phase with each other. XC, has got a negative angle associated with it. So XL is positive 90 degrees, XC negative 90 degrees. So there's our 10 volts. .77 amps, angle 90 degrees. So in complex terms, I is E over Z. Yeah. In this case, that's 10 angle 0 degrees divided by the 26.5 angle minus 90 degrees. Capacitive reactance has got a negative angle. 10 divided by 26.5, gents, is and 0 minus 90 is plus 90 degrees. So we've got a current that leads the voltage in a capacitive circuit. Is that right? C civil, CIV, IL. In a capacitive circuit, current is ahead of or leads the voltage. Okay? Yeah? So we've got these two components that are opposite of each other. If we then introduce a circuit, a series circuit of capacitor, resistor, we know that the impedance of this XC, sorry, is 26.5 ohms, was it? Yeah. What we just calculated, didn't we? Okay. So we got 5 ohms here in series with, and always remember, this is a minus XLJ because we got a minus 90 degree angle. We've got that in rectangular form, and that's got to have a negative sign in front of it. So our total impedance here, with those two added together, it's the 5 ohms. Let's write the formula out. It is R plus minus XCJ, yeah, which is 5 minus 26.5J ohms. Convert that into polar form. 27. What? That's ohms, isn't it? Minus 70. Alright. Now we know the total impedance. We can say that I is equal to E over ZT. We might as well take E, we might as well have it in polar form. That is the 10 angle 0 degrees. (27) angle minus 79.3 degrees. What's the answer to that, gents? So the result of that complex division there is that we got a current of 0.37 amps at an angle of 79. Does that fit in with civil? Positive angular current to voltage, current lead and voltage? Yes, it does for a capacitive circuit. Does it fit in with the original phasor diagram I drew? I'm showing a voltage minus 79.3 degrees behind the current. Therefore, the opposite of that is that the current's 79.3 degrees ahead. Okay? Everyone okay and happy with that? No. We could go on and do parallel. Essentially, we're going to see similar results. We go through that complex arithmetic that we did before. We're only going to prove the same thing as we've just done. We could do that. What I want to do is just go through a series RLC circuit and also show how Kirchhoff's voltage law is complied with in terms of this type of circuit. So I'm going to do an AC circuit on the fly. We'll stick with our 10 volts (60 Hz) if we need it. Going to have a resistor, an inductor and a capacitor in series. Yeah. We've got one current I through all of them. Okay. We could say that we got a voltage VR, a voltage VL, and a voltage VC. Okay. Also, what we'll have is 10 ohms, 6 j ohms. So I'm going to give you the impedance, or the impedances straight away in complex form, and minus 4 j ohms for the capacitor. Okay. Now what I could do here is, one thing I could do is a phasor diagram impedance. So we got three impedances in this circuit. I've got a resistor where I need to draw the line equivalent to 10 ohms long. If I say this is my x-axis starting here, where would I draw the resistance? What's the phase angle associated with the resistance? 0 degrees. So it would go left to right there. Yeah. Then I've got 6 ohms of inductance. What's the phase angle associated with inductance? 90 degrees, positive. So XL, that's 6. R is 10. XC, what's the phase angle associated with that? Down. Downwards, 90 degrees down. That's only 4, so we draw a slightly shorter line. XC. Okay. Now, the overall impedance is all of those added together. Yeah. So what we get actually with reactance is the overall reactance X is a line up here that is 6, take away 4. So we end up with a value X in there, and that is equal to XL minus XC. The difference between the inductive and the capacitive reactances. Always in that order. You always take XC away from XL. So then we create a parallelogram between the overall reactance X and R. That is our total impedance ZT for that circuit. That's the phasor diagram in terms of the impedances. So as far as a formula for the overall impedance of this circuit is concerned, ZT is equal to R plus XL minus XC J ohms. When we talk about a circuit with only inductance in it, we got a positive XL. If we only had capacitance in it, it'd have a negative XL. If we've got both, that part could be either positive or negative. The circuit could be overall inductive, or it could be overall capacitive. What is this circuit? Is it overall inductive, or is it overall capacitive? Yeah, because XL is bigger than XC, this circuit will behave as though it is inductive in nature. So in terms of civil, we would expect current overall in this circuit to lag the applied voltage. Even though it's got a capacitor in it, the reactance of that is smaller, therefore the inductor is going to have a bigger effect. Okay? So we haven't done that phasor diagram. We'll now go on and do some calculations around that circuit. So ZT, as we've already said, is R plus XL minus XC J ohms. Okay, so that's going to be 10 plus 6 minus 4 J, which is 10 plus 2J overall. Yeah, ohms. Okay, what I want you to do, 5 minutes, calculate the current flowing in that circuit in polar form. So well, in fact, I want it in rectangular and polar form.